Okay, welcome back. How are you? Feel all right? Everything's fine? No, really? Like 99% people don't think they feel good. Any questions from have you gone through 2 weeks by now already? Is that the case?
Is really
Just 1 week? Have we done 2 weeks already of the semester? Holy shit, okay. All right, we'll see if we get to the activity. Any questions from previous classes? Yes.
I asked you about technology from
Yes, okay, cool. Yeah, thanks for reminding me. When are we gonna see that? We're gonna see soon, but probably not today, but yeah, let's keep that in mind. Indeed, that will be one of the first divergences we will encounter in quantum field theory, which is not a bad one. And there are several other bad divergences that we will learn how to fight against. You're not prepared, right? You haven't trained yet. So if you encounter, you're dead. You have to train before you get an enemy. Yes, thanks. Any other questions? Okay, good. So let's continue our journey.
저 이제 그 피스코페 임스코 할 때 그게 이제 그 다이버전스 그홀
Yes.
single there's branch you have there's branch called the infinity, but I'm not quite sure about
Which is infinity? The branch code is infinity? Oh, the branch code is infinity.
point as infinity. I'm not so sure. I calculated.
You have to take some limit to see that. Okay, we can talk about it. I briefly checked, and I know it must be true because the fact that we can even take the branch cut like that. So the question was, we had this energy, it's get rid of the p squared plus m squared, there's 2 branching points, and then I also mentioned that there are branch points at infinity when p goes to infinity. And branch cut is defined by connecting to branch cuts. Branch cut is defined by connecting two branch points, right? So the fact that we extended our branch cut to infinity like that, if you remember, that means that there's branching point at infinity, and it had seemed to have a question. We can talk about it, but you should convince yourself. But I think I'm pretty sure there should be. Okay, any other questions? Good. So what have we tried? We tried to naively mix the quantum mechanics with the special relativity with them. And then we say, okay, looks like whenever we try to smash quantum mechanics with special relativity, it looks like there must be no kind of work particle state, right? And then we say, within the quantum mechanics language, meaning the operators and state and Hilbert states, what might be the reasonably good description of a many particle state? And then I show there is just a specific Hilbert space known as a Fock space, and it can be constructed in the occupation number basis rather than keeping track of individual particles. I mean, there's nothing wrong with keeping track of individual particles, but it becomes very quickly pretty complicated. Okay, and not so much useful. So I developed the formalism of a Fock space. By saying that at every point in the momentum space, we have a set of, did I introduce alpha already or not? Did I only introduce A? Okay, so I think I did. So every point of the momentum space, we have a set of harmonic oscillators like that, right? And then from this, we can construct it Hamiltonian. So then I can quickly make it Lorentz invariant version. And let me just call alpha the alpha degree in case I have not introduced already. Then I will put factors of 2 pi cubed. Basically, I'm just scaling this guy by multiplying whatever square root of this thing that appears here, 2 times e, and then delta k. And we talked about the fact that this is the Lorentz invariant delta function, 2 pi is a convention, so I can literally rescale each of the a's to get alpha. And then Hamiltonian, therefore, can be constructed. We talked about, first of all, didn't have put. So let me write in terms of this. There's a pi one that. This, and then there's a momentum operator. Similarly, we can do this because this itself is what we call number operator. It counts number of particles, not just the quantum excitation, but it counts number of particles at momentum p. And obviously I'm solving over all energies, assuming each of the harmonic oscillator doesn't interact at all, right? This is just the sum, assuming everything is completely independent. That's what we do. Then we say, okay, many particles stay in this picture, like P1 to the Pn, can be constructed out of the vacuum by just acting with this great analysis operators. In this case, with the and so, and then such constructed state, for instance, let me just look at the one state, one particle state, then obviously normalize according to relativistic invariant delta, and so on. So we talked about this. Now, just notation. Hopefully, you already. I heard some sound. Was there a question? Okay. Hopefully, you notice that sometimes I put like vector p, sometimes I don't. Okay. Hopefully, you sort it out. When I don't put, so here's the notation part. As we know, on shell particle, it carries only 3 data, which is 3 momenta, right? Because on shell, it's not like 4 full momenta are not all independent because p squared is constrained to the m squared, right? So either I can decide to pick particular 3 momenta that's labeled state according to those data, or I can just write this, remembering that this condition has already been imposed. Okay, no matter what I do, I mean the same thing, but I can just use slightly more free notation. Is that clear? Again, I can solve this equation and just pick 3 independent information, label the state according to that, or let me just write down 4 momenta, but I remember that this condition is always there together. Okay. So when I write this way, for instance, that's what I mean, right? Even if I just write P and Q, that vector sign, that's what I mean. Okay, so this is what we talked about. But then I also said that this formulation makes the Bosch statistics automatically true because this is all commuting operators, right? We talked about them. So now I'm going to talk about the Lorentz transformation property of this creation and annihilation operators. And then I will move on to construct now scalar field. First motivating why we might need to talk about the scalar field. And then we're going to construct a scalar field which is consistent with the Lorentz invariance, causality, and incorporate the quantum mechanics. Okay, so that's what we're going to spend time today. All right, so let's talk about Lorentz transformation. So for now, let's focus on, as we have done so far, let's focus on scalar particles. Obviously, if I say that, you might say scalar particle as opposed to what? Because we haven't talked about anything else. So eventually, when we discuss Lorentz representation of a Lorentz group or Poincare group, okay, we will learn that, as you probably already know, there are particles which are classified according to 2 quantities. One is the mass, m squared. The other is the spin, J or S. Okay, so Poincare transformation, Poincare variance. So this is the representation of Poincare group. All those irreducible representations of the Poincare group. Don't worry about it if you don't understand what I mean. Meaning there are this Poincare set of Poincare transformations that we want to satisfy, and then there are states which, is allowed by all those transformation properties, and those states that are allowed are classified, meaning it's organized according to two quantities. One is known as spin, the other is known as mass. Right? So mass, you can imagine whatever mass, like electron 0.5 MeV, top quark 173 GeV. All right, there are different masses. And then there's another quantum number, which is the spin. So when I did scalar, we're going to spend a lot of time just focusing on scalar throughout this course, in the first part of the course, just to get the concepts right. Okay? So what that means is spin is 0. Obviously, we can talk about spin half. Best example being electron, it is up and down, spin up and down. And then we can talk about spin 1 particle, best example being photon, he has 2 polarizations, all right? But you might, oh, it's not spin. There's a subtle part, which we will have to deal with it. And then you can keep going in principle. Is it can we still? So we know this guy. This is graviton. We discovered the gravitational wave. Yes.
교수님 그 M 스퀘어라고 쓰신 이유가 있나요? 혹시 음수의 M 스퀘어도
This is J. Sorry. You talk about this?
위에 있는 M 스퀘어.
S가 왜 M 스퀘어?
왜 굳이 M 스퀘어라고 쓰신 이유가 혹시 음수의 M 스퀘어도
Good. So the reason why I put, I mean, here I haven't specified whether this is positive or not negative, right? Or not. But M squared is the correct Lorentz invariant quantity, as we know. So M, we loosely just use the mass, but having in mind that I meant this. But I'm just giving you information about this positive part of it. Your question is, what about the negative mass? Negative mass itself, okay, there are some of this. For fermions, the sign of mass sometimes is unphysical. You can always rotate away the sign of the mass by what's known as the field redefinition. We will get there at some point. Maybe not this, I don't know. All right, there's that. For scalar bosonic particles, mass parameter always appear in the field theory in this form. Therefore, here the question is whether this side, this itself is positive or negative. Negative mass are allowed, provided you have another term in the action or another stuff in the theory in such a way that naively the negative mass means that, oh, it looks like you gain energy by producing this particle instead of costing energy, right? If you have a positive mass energy, in order to create them, according to Einstein's relativity, I have to put energy to create that guy. But if you have a particle with a negative mass, which means that, well, you want a particle, pay me, right? Another one, pay me. So it looks like this system has instability, meaning instead of the ground state without having any excitation being stable, meaning that's not a ground anymore, because theory prefers preparing explosively a lot of particles, right? So theory will go crazy, and this sort of a feature is known as the instability of the theory. So sometimes you can cure those instability easily. Sometimes it can cause real big deal, and you may fail to cure those problems. So if you cannot cure those problems, you cannot have a well-defined quantum mechanical description of the system. You fail at some point. So the overall answer is there's no universal answer. Fermion, maybe some physical, scalar boson, maybe it's fine to have a negative M squared if you have some other stuff to cure that problem. Sometimes you fail, then you have to give up on that problem. Okay. So again, scalar that we are going to focus on, but we are going to eventually have to talk about this. This we are not going to discuss much or not at all probably. This is the graviton, gravity waves, and this we haven't discovered in our universe yet, but can be there, known as the superparticles. If there is a symmetry known as supersymmetry. But again, we are not going to discuss this much. So most of the time, we will spend a lot of time with this to build up a lot of conceptual part. And then once we are on top of those concepts, and you're confident that you're not going to shake because of the concept issue, then we will extend to include these particles later. Okay? So for now, therefore, let's just focus scalar particles. And when I say that, I just mean that under Lorentz transformation, it doesn't have any spin degree of freedom. It has just a single spin degree of freedom. It doesn't pick up any base. That's what I mean. don't worry too much about this part of the discussion because I have not constructed anything. I just told you the answer, right? So we're gonna have time to actually construct those parts for sure. So let's go back about Lorentz transformation property of these alpha and alpha. Alpha and alpha. All right. So how do I know? So scalar then. The quantum state of scalar basically has only momentum index, as opposed to, for instance, momentum and then spin information. If I have to talk about extra spin department, right? So scalar doesn't need this, for instance. I don't need to specify which spin state I am in. In addition to that, in principle, you can also have P more generally, spin, and say some other information, quantum numbers. This is obviously momentum. Energy momentum, this is spin, and it can have other multiplicity. If there exists what's known as internal symmetries. Internal velocity, which we will cover. In other words, what the last thing means is that suppose I have the scalar, so drop the sigma part. Somehow there are another scalar which will look almost identical, but nevertheless it is different. And then there is some relation that is connecting these two guys together. Okay, we say that there is an internal symmetry. It is not about the space-time part, but nevertheless I can say that, oh, this guy almost looks like me, so let's combine them together and then treat it as a single guy, meaning they can rotate each other, they can change the structure of themselves. So that happens when there's below symmetry, that there can be extra multiplicity. This we will spend some time talking about. All right. So for now, scalar, single scalar. So let's drop everything, and then we just use single scalar. Just P. Okay, so that is actually easy to formulate and understand the transformation property of these guys. So suppose consider P. And if you apply the Lorentz transformation with the operator U of lambda. So there's some Lorentz transformation lambda. This is quantum operator that incorporating that in the universe. And this obviously should give rise to say the lambda P, right? There's a momenta, and if you rotate momenta, you should go that way, right? So it should be lambda P. Now this was alpha of P creation acting on the vacuum, right? So this equation can be written as follows. If I take lambda U of lambda acting on P state, that should be lambda P. So that's what I mean by this equation. So let's take this equation, apply to the definition of the state that is given by this. So that means, let me just rewrite U of lambda alpha P acting on vacuum. I just rewrote this line. Right again, lambda P dagger U of lambda dagger U of lambda. I just inserted the 1 because it's a unitary operator. Excellent. Good. So far so good. Now, probably I said at least once that in this course we will demand that this is true. So now let's understand the physics meaning of that condition. What it means is that the ground state or vacuum of our quantum mechanical world is invariant under Lorentz transformation. I just literally said by this equation. So vacuum is invariant under Lorentz transformation. And there's a slightly fancy way of saying this. Even though theory may respect the full symmetry, sometimes it is the case that the vacuum state or ground state may not respect the symmetry, which means that vacuum or ground state may not be invariant under some symmetry transformation. In that case, we say that the given symmetry is being spontaneously broken. Okay, so I'm not going into that in detail yet, but at least I'm just telling you the concept. All right, so another fancy way of saying it is that Lorentz symmetry has not been spontaneously formed. So we are focusing on quantum field theory that satisfies this property. If this confuses you, drop it, just take this. Vacuum just is invariant Lorentz transformation. All right, so with that assumption, then we can just get the following answer. Somehow I'm sliding towards. So yeah, this leaves that. Then I get. And I know from that equality, so let me just say it's star equality. That should be equal to that guy, but that guy can be written as lambda p dagger acting on the bracket. So by comparing these two, I learned how my creation operator has to present. So I get that U dagger alpha p dagger would be alpha dagger. Meaning take this creation operator, which is function of momentum, do the Lorentz transformation as if it is a joint representation or similarity transformation. If that works better for you, then it turns into the creation operator with the lambda p. Physically makes sense. Right? Obviously, if you start including spin, there's a little bit more entangled story. There is a little bit more story than that, but at least for the other is true. Now, take the Hermitian conjugate of this equation, and you get immediately get equation for Niles operator. Okay, good. What about the translation part? So this is Lorentz. What about the translation? Well, we can work it out. First of all, we already picked the basis of our quantum state to be momentum state, which means that momentum translation. So how do I write translation operator? Identity times A. So here, when I wrote U of lambda, I meant Lorentz transformation part, and then translation being 0, right? So that's what I wrote there previously. So this is equal to I eta A, where P is the momentum operator generating translation by the size of H. Now, the fact that we are using momentum eigenstate means that we already diagonalized this operator. Okay, because by which I mean, let me just write in terms of this. Let me set that. By this I mean either I, eta A, acting on momentum state is obviously just I momentum. Now this is number. So that's what I mean by diagonal. I mean it is an eigenstate. Okay. Now we can understand how alpha dagger transform on the translation immediately from this equation. Okay, so let's do it. So e to the I p a p. But I can rewrite this as dot a alpha d dagger acting on the back. That assign enough space. Then I can put it there. Insert it in 1. And then again, I'm assuming that the vacuum respect the translation invariance, right? It doesn't change. So in other words, our vacuum doesn't, our theory doesn't break translation spontaneously. All right, so then this is equal to A alpha p dagger vacuum, but again, the star relation tells me that it should be either I, now number P times alpha integral vacuum. So by comparing these two, again, I see that, let me save my time by just boxing out. Again, operation by conjugation. Oh. I mean, too much, right? Stop here. So creation operator acted with the translation generator. It's the same as itself, but picking up this space. So he knows about, how much it has been translated. Again, you can take a Hermitian conjugate of this equation to get the exact same formula for annihilation operator. In that case, so if you don't include this dagger part, then you should get your minus sign, right? Because if you Hermitian conjugate that, this is the number, right? You pick up the minus sign here. So it's a math. It is algebra, but hopefully, you got what I'm doing here. So we constructed Hilbert space, which is now, suitable to. It's ready to describe many particles phenomena. Okay, and for that matter, we introduced a set of creation annihilation operator, but I just for a scalar particle. I just show how they transform under Lorentz and translation, basically full set of Poincare transformation. Okay, this will be now used immediately now to construct the scalar field. Okay, so question. Okay, so now let's actually construct the scalar field. By the way, you might notice that I'm picking a lot of stuff from Coleman's QFT, right? I never studied it before. I'm just start reading it because I was looking for any book that fits into somewhere middle between Mansworth and Weinberg. Because Mansworth is great, I just studied it, but I just wanted to inject more challenges on you, more pain on evenly. But then I didn't want to make all of you to give up on your career either. So I could not just pick Weinberg. So I wanted to find something that fits in the middle. I found it Coleman really fits into that and beautiful. So I even suspect, I don't know, you guys can figure out. I don't know whether I think Coleman is senior than Weinberg. Which means that probably Coleman's book is a precursor to the Weinberg probably. So my feeling is that Coleman laid out all this thing from a physics intuition, and then sort of his humor and circuits. Anyway, then I think Weinberg, probably as a junior, but who had trained with strong math rigor, just cemented it with the more mathematical rigor. That's my feeling. So I think you can get a lot of physics inside. By actually reading through Coleman. I really strongly recommend. Good. So let's it's funny. Also, Coleman is known for, I think I told you already, physics, which means that there's a subtle and difficult topic developed throughout the history, which is being done now too. And whenever such a thing happens, there are always a couple of people in the world, but not many, sitting at the cutting edge of the development. And has chance to first understand those developments and then start explaining those to other people. And Coleman is known for his ability to put very subtle, complex subject into trivialized level. Meaning somehow he knows how to make, this is fancy, it's maybe blah, blah, but it's trivial like this. Which means that he really used a strong physics insight to get that point. Okay? And you need a both. You need both like explicit calculation, but also now you have to bring your insight. I don't know, first bring or later bring in, and let's do it. So then I start seeing the path in a more trivial way. So I was enjoying a lot this part, so let's do it. So now we're going to talk about constructing proposal. Yeah. All right, so how are we going to do it? We're going to first ask the following. So let me say in words. Since it is describing Coleman, I guess it's okay if I see it. If needed, I'll start drawing. So previously, the first part of the lecture, right? We say, let's take a particle which takes a relativistic energy. And then I say, I'm just going to try out the quantum mechanical formulation of that, just replacing Hamiltonian with scale root of physical plus m squared. We did that. And then we found, oh, okay, so then there's the causality issue, and then we say, what was wrong? And we try to say, can we just localize this particle? In order to even ask the question of, causality violation, we say there should be a well-defined notion of a position operator, right? Because how are we going to even ask the causality if you don't even have a notion of a position? So we say, oh, there's a well-defined notion of a position operator, and then we did a Gadakian experiment of measuring this amplitude outside of light column and see whether it vanishes identically or not. We found it doesn't. So then we say, oh, there's this problem, intrinsic problem of even asking whether we can localize the particle. How do we do that? Take the cylinder, put a single particle relativistic, and press, so that we enforce it to go into the smaller region in delta x, right? And see if we can localize. And then we say, as you shrink the delta x to 0, at some point delta p goes to infinity. So we have much more energy budget. We start producing a whole bunch of more particles. That's where it's starting failing. Now, so conceptually, this way of asking physics question is a sort of a Schrödinger picture. There is a particle state, right? There's a particle state, and then we say, okay, can I then by the way, do you learn Schrödinger versus Heisenberg picture in quantum mechanics? Okay. All right, but not interaction picture, yes? Sorry? Interaction picture too? Wow, okay, good. So you already get it. So Schrödinger picture, just to remind, state evolve, operator state. Right? Operator doesn't. But the product, therefore, there's overall single time revolution, right? And in Heisenberg picture, state is the time independent, operator evolves in such a way the product evolves the same way. Okay, good, done. Okay, let's not go into the interaction picture. Then I said that this asking localization of particle question is more of asking question in Schrödinger picture. Is there's a particle, a state, and then we say, well, we can actually localize the notion of the state somewhere in the space-time patch. But then there's a Heisenberg picture version of this question, which is to say, okay, can I localize a measurement of observable? What is the measurement of observable? Observables in quantum mechanics is the operator, which is Hermitian. And then when we ask the question of whether there's one observable being made here, another observation being made here, we're talking about whether there's an operator that is acting this part, there's an operator that's acting this part of the thing. We can ask the question about the causality of this configuration. Okay, so we're going to proceed that part from now on. So what we're going to ask is that consider this space-time patch. Okay, and then we're going to consider two patches in this space-time. So I'm going to consider a patch which I call region number 1. I'm going to consider another region which is called region number 2. And they are, as you see from this drawing, they are space-like separated, right? So region R1 and R2 are space-like separated. And by which I mean for any point x1, which is a part of this region number 1, and any x2 in the region number 2, for all those combinations, x1 minus x2 squared is less than 0, meaning space like separated. So these two patches are causally disconnected. Meaning there's no way to send any light signal or any information from patch 1 to patch 2. Because in order to do so, you have to have whatever signal that travels faster than light, which is impossible by causality. Okay? So they are causally disconnected. Now, the question that we are raising is the following. So in usual quantum mechanics, by which I mean consider non-relativistic sense of quantum mechanics. We were instructed that if you have a set A, which is a set of entire permission operators. So this is an entire set of permission operators. We were instructed in quantum mechanics class that for any such permission operator, there should be a notion or concept of observable associated with this operator of A, of O, I'm sorry, and then there should be measurements. Right, so that's what we were taught. So, for instance, good example is there's a sigma x, sigma y, the spin is I times sigma z. So this sigma x, sigma y doesn't commute. Nevertheless, no problem. So electron comes in, you first do sigma A measurements, the electron is in sigma x eigenstate. Right? Either x spin up and down. Then later, okay, let's do sigma y measurement. Then this measurement can now be put electron in sigma y eigenstate. Right? Even if they don't commit, nevertheless you can talk about measurement of each of those operators. No problem. It's just that you have to take into account square root of 2 properly. Right? This thing is square root of that minus that. You have to take that properly. But nevertheless, it is doable. Now, the question, now in the context of adding quantum mechanics with relativity is the following. So, contextually, we are asking, now, let's put it in special relativity. Okay? In particular, Lorentz invariance and in particular in this discussion, causality. Can I take still the same exact entire set as all relativistically measurable observable, or only some subset of that will survive? That's the question. Because there's a syntactic, there's a tension. If so, if whatever that is allowed to be quantum mechanically measurable, consistent with the causality, what is the condition that needs to be imposed on this set of operator to be here? Right? That is the question you're asking. Is that clear? Okay. Take 3 seconds to process.
So you're talking about whether a Hermitian operator can be causal, the condition of Hamiltonian operators to be causal.
Yes. So good. The condition on permission operators to be consistent with the causality. That's the question. So in order to digest this thing, let's consider another experiment, third experiment, which basically Coleman presented. I'm just saying it. So consider there are 2 observers. A is Alice, A, and then there's Bob. So there's A and B, 2 observables. Okay, and then there's a room, and then Alice went into the room, and then measured sigma x and electron prepared in that room, and then Alice saw some result. Alice left the room. Bob came in, did the sigma y measurement. So now the state is not anymore original sigma x eigenstate we turned it into. Alice came in. See, oh, who the hell did this? Somebody came in and modified what I did, right? So Alice's result has been modified due to Bob's measurement, right? Good. So that happened. Now let's ask the exact same question. So now Alice is in this room and still doing the sigma x measurement of the electron. And Bob took the sigma y operator, on the other hand, They went to the Andromeda, another galaxy. And they say, oh, I'm really green, I don't want about what's happening there. You can ask when Bob taking this sigma y operator still can affect what Alice is doing. Right? So in the context of relativity, the question is, in order for the Bob to affect what Alice is doing, Bob should be here, right? Should be causally connected. Is that clear what I'm saying? So therefore, there is an operator here. There is an operator here, maybe something different. So in order for that operations to should affect operation of this guy, they should be in the causally connected patch. Otherwise, Bob can never send his output or whatever input to the Alice's patch faster than light. So therefore, putting everything together condition is followed is this. So consider two permission operators. So O1, O2 are both permission. Now, in the context of the relativity, then there's a notion of where that operation is happening now. Okay? So therefore, O1, O2 operation should not affect each other. That's what I mean by equal to zero when they are happening outside of the light bulb, meaning they are causally disconnected. Okay? So Bob never enter into the room where Alice is. That's what I mean. Okay? So this condition is sometimes known as micro-causality. Okay. But before I move on. Yes.
Is there macro causality condition?
Is there? Oh, good. Good question. I mean, you gotta ask. Why micro? I believe the macroscopic version of the story about the causality is known as cluster decomposition principle. So let me say the thing. What is a cluster? Cluster means clustered, right? Decomposition principle. Decompose means that they factorize. So instead of writing them to say, if you're curious, you can look at the chapter 4 of Weinberg. So that I cannot help. But I can at least say in word. Suppose there's one experiment happening at here. Good. So here, right? I'm giving you a signal, you're reacting, there's one experiment happening. There's another experiment happening at, say, Harvard. Say, Professor Matris is giving a QFT lecture to his student. Okay. And when I write down this, obviously, the chance that he misspelled his stuff on the board should not change. Right? In other words, if I write this bigger, obviously he started making more mistakes there. That doesn't make sense, right? If this is happening exactly at the same time. So the statement is that there's a one process, physical process happening here. There's another process happening here. And there's a probability for each of those events individually to happen. Then the probability for these two events simultaneously to occur should be product of individual probability if these are causally disconnected, meaning they are independent events. Right? Statistically, they are probabilistically they are independent events. This is the notion of two clustering decomposed if they are causally disconnected. Okay, so that is notion of a cluster decomposition principle, and this is enforcing every single bit by bit. Okay, so this I think guarantee that the cluster decomposition is satisfied. Yeah.
So by writing that continuation, are you saying that the O1 is the O1 axis affecting, that's the action of the O1 or O2, you're saying?
So this is an operator equation. This is a commutation and relation of an operator. But I'm saying if this operator equation is satisfied, then the physics situation of this thing will satisfy causality. Meaning, if you have a state trying to measure something with this guy, and then ask whether if you measure that guy, something changes or not. In other words, let's run the exact same thing here. So let's prepare electron. Alice is measured per electron with the sigma x operator. She got some eigenvalue with sigma x. All right. And causality in first is even if Bob measures the same thing, right? Since they commute, Alice will see the same answer. So result has not been changed. The result has not been modified. So long as they satisfy this, it is outside of the line. So this equation is an operator equation which guarantee whatever physics equation I explained will satisfy. Okay, good. Let's move on to constructed scalability. So why that field? First of all, why did the field that? Field, well, let me just answer that question before introduce what I mean by it. So in previous discussion, recall when we talked about phase, which is good for many particle physics, we talked about like P, which is alpha P dagger O, and so on and so forth, right? So all things, for instance, this, anyway, all of that, everything here is in momentum space representation of the physics. Right? So there's a momentum operator, there's momentum dependent operators and state labeled by momentum everything. Now, in order to, on the other hand, incorporate this causality condition, right? I need to have something which is a function of a space and time. Otherwise, how would I even check? Right? There's x1 and y, how would I check? So therefore, causality, or to incorporate causality, we need, I don't know, whatever it is a function of a space and time. We need some we need a position space object, right? Then I know I can use that to check causality, as this equation is clearly shown. So I need something is a function of x, which is constructed on the other hand in terms of disguise, because I know that this is good object. So I want to use that to construct position space object. Then I can ask a question about the causality here. Okay, so that's the sense that it leads to the point that manifestly causal description of many particle physics seems to require that we want to introduce quantum field. Now, pictorially or conceptually, you can think of this as at this point of space and time, you assign some sort of quantum value. Okay, there are points where there's any excitations, meaning there's no particle creation, nothing is there. There are some points where you can actually act with alpha p to create a particle at the point. So particle design is described in a sense there's a field, there's a ripple created by alpha p. You interpret that as a particle being there with some momentum p. Okay, so let's now determine the structure of this thing. All right, good. So we're going to impose the following conditions. I'm following Coleman, although some bits may anyway can be, I think, improved, but that's already masterpiece. So let's follow. So there are conditions I'm imposing on the structure of the five maps. So first of all, I want to say that this field. Let me consider a single scalar. Okay, so this is nothing but causality condition at the level of this particular scalarity. This is causality. So for this case, I assume that it's Hermitian. But therefore, it makes sense that since it is Hermitian operator, it can be observable to the extent that it satisfies this causality equation, right? As we talked about. On the other hand, in principle, you can consider non-Hermitian field, and indeed, we will consider non-Hermitian field in this course. For instance, there can be complex scalar field rather than real scalar field. It exists. It's important. That's the case. For instance, also there's a fermion field. All of them are not Hermitian. So we will have to talk about it. But the point is that non-Hermitian operators can always be factorized into Hermitian and anti-Hermitian bits. Decomposition always exists. In each of them, basically you can apply this logic. So you can think of this discussion as a minimal building block. And then any operator that appears in the quantum field theory, you can always factorize properly into this discussion. Okay? 3 and 4. So these are our concrete variants. Concrete transformation property. So first of all, IPA. Then okay, so obviously you see that, oh, whatever that means, this is performing space-time translation on this. So yeah, it should be something like this. But the only question is this plus or minus? Right? That's sort of that's good. And this is 2. Whatever this is, I'm performing Lorentz, like either rotation or boost on this field. So what the object should be, the field with Lorentz transformation performed on space-time sense, right? So at this level, it makes sense. But the only question is, why this is minus sign? Why this is a lambda inverse rather than just lambda, right? So that might be what you are going to care about. So let me just sort it out real quick, and then we can proceed. So the translation part. Am I too fast, by the way? A little bit, okay, so calm down. I've been excited to say for like more than a week. So I need to literally, like, there's a lot of things that I had to be excited to say, meaning operate a lot. And so I'm turning off my frame frequency for a little bit now. Let me know when you're ready. Good. I didn't mean to sleep. Don't sleep. I just meant that slow down. Don't sleep. Wake up. Okay, ready. Let's do it. You ready? Good. So let me just sort it out the sign here. Okay, real quick. So here is the x-axis, and say I had an object here at x equals 0. Is this, by the way, it's weird that I'm asking now after 2 weeks, but is it too small? Is it okay to be seen from the back of the class? Oh, you can see this? Okay, good. All right. What if no? Let me do it. So then let's continue. So now let's actually perform a translation by A on this system. So how would that look like? There was the original x equal to 0 point, then I literally moved the object by A. But x equals A, right? So I move A, and this is my, I'm saying, new system. I'm considering this to be my x prime from 0 system. Okay, so I just moved it. In this sense, original x equals to 0 corresponds to the point where x prime is minus A. So if you look at here, yes, I performed it. Original x equal to 0 point corresponds to minus A point. Okay, that's the minus sign. And the second part can also be sorted out similar way. Suppose I had this system with object pointing along the x direction. And then let me make a rotation by theta. So now object is here. Then obviously, original point from that perspective is minus theta angle rotated apart. So I have to rotate backward. Okay? So anyway, so that. So this is to say that whatever the scalar field that I want to construct must satisfy nice and good, well-defined concrete transformation property. That's all I'm saying here. Lastly, like I said here, when I motivated the field itself, this is not independent from all the description that we have gone through so far. Obviously, that is waste of time. So whatever that is, it's going to be construction made out of object we already talked about. So phi will be constructed out of alpha. And alpha is a function of p. Somehow I have to turn it back into function of s. So that's the goal. And then here we assume for now that phi is the linear combination of alpha dagger. So I'm going to write it as okay. So I assume that the phi is made out of alpha dagger with Lorentz invariant measure integrated over all the p to get rid of the momentum dependence. But obviously the function has to have x dependence to turn back into x dependent function. Okay? The only assumption here I made is that it is a linear function of alpha dagger. What's the motivation behind this trial? Well, we want to start from the minimal, like simplest possible object first, linear. And we want to check whether that already start working with the causality and others. If so, we can take this as since my construction is a minimal simplest object, we can take this as a minimal building block for entire other constructions. This may not be minimal object. It may be required to have a non-linear terms too, quadratic. Then we have to go there, and then we take that as a minimal object, and then construct the rest of the observables out of that thing. So hope is whether this is simple enough and a large enough structure so that it satisfies all the causality conditions. Okay, so we don't have to complicate ourselves considering already quadratic because I'm fancy. But then you might be missing, right? If the construction you made is not minimal, then whatever construction you made out of your own non-minimal construction will definitely miss slightly more simpler observables, right? So we have to start with the minimal construction. That's the motivation behind this choice. Okay. Right, so let's do it now. Okay, good. Let's do it. 15 minutes. 20, yes.
So the number operator is not the linear combination of
Good. So this alone, good. The question was the number operator is a quadratic number, meaning it's part of the two. So we can ask, oh, how would the number operator pops out of this construction? Therefore, the question is Hamiltonian, which is proportional number operator, which is a dagger A or alpha dagger alpha. So you see that therefore that Hamiltonian will be a polynomial function constructed out of a box somehow. Right? So at least it fits into the right direction. So long as I can construct all observables as a composite, meaning product of this guys correctly, then I'm okay. The question then is what physically this means, right? We will get there. Any other questions? Good. Okay, so let's do it. Let's do it. So let's start with the equation 3 and say phi of x is equal to e to the I. Would you be upset if I start dropping hat here? Would you be absolutely upset if I do it? Okay, you're okay? Okay. So I'm gonna try to be right a little bit big for the operator. Small for the number, is that okay? All right, good, let's see. X. Okay, so this is operator equation. Here, so let me so this is not independent of the space and point, right? This is 0. So here, I'm gonna write it as the similar construction. So for that matter, let me actually put tilde here, just to distinguish what I want to do here. So this is space time X independent. I know that there's gonna be function of only momentum, and then alpha p, and then GOP, alpha p there. Obviously, we will ask eventually, or you can ask what's the relation of this function to that guy. You will see soon. Okay. Good. So then, so long as I can construct this enough, then I will have to construct back the general operator phi of x. Okay. So then let's ask property number 4. The transformation. So action of the Lorentz acting on phi is 0. Is according to this equation 4 1. This is 0. This is 0. So if you take origin, if you do the rotation, it sits there, right? So lambda inverse of 0 is 0. So then this is equal to the phi of 0. Okay. So basically that makes sense. So let me just write it out. So phi of x, which is that, I'm gonna write this equation. Then these are just the scalar functions. Okay, these are just scalar functions. By scalar, I don't mean not yet. Sorry, these are just functions. Let me not say scalar yet. Okay, just function of momentum. Let's figure out what kind of function they are. We have this. So therefore, they're not getting operated. That's what I mean. These are functions, so they're not getting operated by the operators, right? This is function. So then we get u alpha u vector v okay, so far so good. I just passed, and we already learned this. That was alpha of lambda p. So can you run? Can you run? Because I have state p and then activate the Lorentz transformation. I should get state with lambda p. That was how we derived this equation. Okay, are you with me? Okay. Don't just accept equations. Always attach physical meaning. Then you can get faster. Okay. So state created p, action by lambda, they should give me lambda p state. That was the equation. Similar here, maybe it was exactly the same thing. So there was lambda p there. Okay, so therefore we get good. So far so good. Now I will do this really quick. So focus. Now we got paid off, right? So we trained. This is Lorentz invariant. Beautiful. So I'm then gonna call this guy P prime. This is the same. E3 P prime over E P prime. Lorentz invariant. Okay, and this should be lambda inverse P. And this will give lambda inverse P. Yes? Super so good. So therefore, that equation turns into did I just Control Z? Can you do Control Z? Here. Can you reconstruct my equation? Okay, so right, so good. Therefore, that equation turns into, let's continue here. Then I'm gonna just not drop primes here, okay? Let's just P. And then that thing must be equal to original phi of 0. So therefore, we learned that f of lambda inverse p is equal to f of p, and I know none of you are from math department, so I don't have to say, but let me say, these are linearly independent. What that means is that this is not proportional to alpha dagger. If you were, it is a Hermitian operator. We know it's not because it's going up and down. Remember, ladder operator is a linear combination of J1, J2 with I sitting there. So that's why this should be independent, that's fine. Okay, so what this is this equation here. Now let's extract physics out of it. Am I going so fast again? Because it's clocking. Question. What does this equation mean?
It becomes scalar. Scalar.
Something scalar. Which exactly what scale?
Lorentz invariant.
Good. That means that f and g are Lorentz invariant function of momentum p. Right? Right? Under the Lorentz transformation, the value doesn't change. So f and g are Lorentz invariant functions of momentum p. How can we construct the Lorentz invariant function of momentum p? This should be a function of what? What is the Lorentz scalar you can construct out of momentum p mu? P squared. Good. P squared is equal to what? M squared. Is it the function of momentum or not? Does it depend on momentum or not? No, which means that these two functions, which formally is a function of p, but because of Lorentz invariance, it becomes what? Independent of momentum, correct? I mean, it's M squared. It's a parameter. At least it doesn't depend on any three momentum data at all. Right? So which means F, G are constant. Otherwise known as a constant. Good. So I'm gonna drop just the momentum dependence from now on. Okay. This is done. Okay, so now take this, drop this. Let me do it slightly better. Drop this. Very good. I'm erasing everything. So here I'm gonna put F, G, alpha P there. Okay, so that's all the first part of the problem. Now let's get the general expression for phi x. And phi x can be obtained by doing this operation. So when I sandwich either the IPX, either the minus IPS that pass through acting on this guy, acting on that guy. And we worked it out too already, right? So phi of x f into the I p dot x. Okay. F gotta do it today. V into the I f dot x. Okay, and this we learned is equal to e to the I p dot x alpha p dagger. Now number, don't blame me. Okay, so I have put it there. So this we worked it out, number x alpha p. So phi of x is e to the minus I p dot times number f times this. It's an IP dot plus your number times that. Yes,
In the line next to the number 3,
yes.
there are if plus IPX sine 0, right?
You mean you're looking at this equation
And it should be minus IPX.
here?
Yeah.
So if you're comparing Coleman, he mixes up. That's where you're coming from, or
Or I just okay.
so I'm trying to be consistent, like plus or U minus or U dagger. But if you look at the Coleman book, actually, he will have minus here, plus, and the dagger here, no. That will be in conflict with what he talked about in chapter 2, for instance. I'm just fixing it. Yeah, try to think about it. I can be wrong, but you see, in quantum field theory class, you cannot sue me because of minus sign of vector of 2, but you can ask me. So that's what I think. That's what I think is correct confirmation. But check and think about it. Any other question? Good. Yeah.
그러면 저기 위에 거랑 저기 왼쪽에 3번이랑 안 맞는데
This, and then I first passed it here and did the math, and then just using this result and just wrote it again.
아 그러니까 여기 왼쪽에서는 파이에 마이너스를 오른쪽에 곱하고 플러스를 왼쪽에 곱했을 때
Ah,
마이너스 A만큼 더해진다고 했잖아요.
yeah. Okay, so you're saying if I said, I see. So it should be the other way around. That's what you're saying, right? If I collapse, and then if I pull 0, minus x. I see. So I have to put minus I. Very good. Someone is focusing. So minus, you put in everything. Okay, so he was right. Thank you. I was in rush. So let me write that way. Dagger, there. I fixed everything, yeah? Oh, no, yes, I fixed everything. Okay, now you start running into real QFT business. So figure out minus sign daggers, put everything correct. Okay. Good. Any other question? Good. Now, we have therefore so we used condition 5, 3, 4 so far, right? So assumption of a linear combination, translate Lorentz invariant, put us to this much. So now let's move on to apply 1 and 2. 1 you remember, it's gone. We have to remember. So let me just rewrite it. Oh, I can use this space too. And I'll cover this. Okay, so 215. What does that mean? All right. Okay, so does that mean that I can stretch, or does that mean I have to go up? So next time, what I'm gonna do is to apply the condition 1 and 2 and show that this cannot be random because constant. There's an important relationship that they have to satisfy, meaning causality constrains the possible choice of F and G. That's what I'm saying. And then we are going to check only then, by construction, this field can now incorporate the relativist causality. So as long as you use it, you are free to not to worry about causality problem, right? Because we constructed a minimum building block that it already incorporates the causality in it. So if you do have a formulation in terms of that, then most of the time you will satisfy causality. I said most of the time because still, even in terms of this phi field, you can still mess around. Like it's an instability issue you can create and so on and so forth. Right? And after that, we start talking about scalar field use. All right. That's it for today. If you have a question, you can ask me now or after. All right. I'll see you on Wednesday.